Hello my friends, welcome to my tutorial. In this tutorial we will run an Ansys Fluent simulation of a simple conical nozzle, but this time in 3D geometry. The nozzle will be identical to the one from the axisymmetric case. So all the conditions that are required for a Wakefield accelerator are the same, so are explained here. This tutorial will be shorter because as you will see, we will reuse many steps that we had in a 2D axisymmetric case. It saves a lot of time if you do like this. And I want to stress that there is no reason to simulate this type of nozzle in 3D instead of 2D axisymmetric. The results are the same. I'm showing you all of these all these steps just to learn how to prepare a simulation of a 3D gas target. All right, so let's get started. So this is the last case that I prepared for a 2D axisymmetric simulation. We will reuse it, so all you have to do is just left click here and duplicate. So this will duplicate this case accepting the solution. Alrighty, and now let's give it a name. So 3D conical, let's say. Okay, so let's open the geometry. Alrighty, so this you recognize this shape from the last tutorial. So now we don't need the surface, so we can delete it. Right click and delete. All right, and we go to create, revolve, and now here we choose the geometry, so the geometry will be this, and apply. And now we need to define the revolution axis. So it will be, so if you click this one, if you click on this one, it will show you in what direction it will rotate the geometry. So we will need this one, apply, and here add material. The direction you don't change it, and here you can do it partially or full rotation. So depends how you need for your simulation, and press generate. And this is the nozzle with inlet, walls, and this is the outlet. Again, if you need at this point, so if it's a new nozzle, then you will need the distance from here to the outlet, which is here. So you are using tools, analysis tools, distance finder. So we will choose this edge and this edge, and the distance is 17,196, so like before when you checked into the axisymmetric case. Write this down because this will be necessary when you take line outs above the outlet. All right, so we finished this one. We can close it. Everything is okay. We have the check mark. Okay, let's open the mesh program. Now we wait to update the geometry. Alrighty. So here it complains about this the name of the boundaries because it's a different geometry, so he doesn't recognize here. You see here an XXX, that means you have to redefine them, which we are gonna do now. It's easier. So click this one, click on pressure inlet, selection, and here check surface, click on this, apply. All right, we define the inlet. Now let's define the outlet. So for this one, we need to choose multiple surfaces. So if you click this one and keep on the keyboard Control pressed, now leave the control, don't press Control anymore, rotate, all right, and single select, again press Control on the keyboard, and you have three faces, so you have it here. And of course we don't have center line anymore, we can delete it. All right, now at mesh we can delete this one just to avoid any confusion. So here when we mesh, we will have to use two different meshes on the surface and in the volume. It's not absolutely necessary on the surface, but it's good to have it because the quality of the meshes is much better. So right click on mesh and face meshing, okay, geometry. Then since it's a surface, you have to click, you don't have to choose here, it's automatically chosen. Click on this one and Control A to select all the surfaces, apply again. When you choose here surfaces, you can choose all of them or just some of them if you think you need only on one surface. I chose all of them because from my experience it always works. Okay, and now again right click, insert, and choose method, geometry, so this geometry, apply, and now we choose the method from automatic to multi-zone. So what this is, this multi-zone will fill the entire volume, in this case with instead of squares like in the 2D axisymmetric. In 2D we will have cubes or distorted cubes. So there will be hexa cells. All right, and now let's go to mesh and we choose this one to be about 4. Let's see, we will choose now, and depending how many cells we will have, we will decrease it or increase it. All right, sizing, we don't have to change here anything. At quality, let's make sure that we have smoothing high. And we have statistics, so here we'll see the number of cells. Okay, now let's right click and update. And now the meshing process starts. You can see here how fast it is. Okay, so here we have 45,000. It's not quite enough. Let's try 3. So you should have a few hundreds of thousands of cells to get an accurate result. If you don't have enough cells, the simulation might not converge properly. So the mesh most of the time will affect the quality of the simulation. So you have to be sure that the mesh is done properly. Okay, so 86,000. No, I don't like it. I want Let's put 2. So now it takes a bit longer because there are more cells. So 261,000. Yeah, it's fair. Yeah, I will try on 1.5, let's say. So always after meshing, check the smallest volume that you have here, so the smallest volume of a cell. Because if you are trying to, if you have shocks, for instance, and they are micron sized, then you will not be able to see them in your simulation if the mesh size is not properly chosen. Okay, 500,000. Okay, we finish with this one, and we can close it. We open the setup. Now the good thing is in the setup, so here you choose the number of processes that you want to run in parallel. I chose 62. It doesn't really matter now. It matters just for you when you run the simulation. Remember, the maximum number is for Ansys Student version, which is the free version, is 4 processes. So if you have 4 cores, you will have 4 processes. If you have 6 cores, you can choose only 4 processes. All right, now we import the geometry. It's imported automatically. We need to wait. Now you will have some errors because we had different settings before, different geometry. So of course it complains. We can close this one. Okay. So when you have this kind of error, don't worry, just press enter and that's it. Okay, so scale again, make sure you have in millimeters just to see it properly, and you have all the dimensions in millimeters when you export the data. Check. Everything is fine. So the minimum volume here you can see it's 1.2 10 to minus 15 meters cubic meters. So it's quite small, and so you can see even more. So the domain and all sorts of statistics you have here. Okay, report quality. Again, it will tell you the quality. So if you need to understand or to learn more about what quality means, just check the documentation of the Ansys Fluent. Okay, so here you have details and units. Again, it kept the units that I defined the last time. So in atoms per cubic centimeter, it's more relevant for what I'm doing instead of kilograms per cubic meter. All right, now the models. So we have here the solver. It's again density based and it's a steady simulation. At models, we will not change anything. Just make sure you have energy on and viscous SSTK omega. Inside is the default. If you know what you are doing, you can change all of this. Again, check the documentation by pressing help, and it will open an online page which contains all the information about this window. So each window has help, and if you want to see more details, you will have there. You can click and you can check what does it mean, you know, all of this. Okay, so here we don't have to do anything. Materials, it kept the same material as before, so we defined as helium. Now if you have here many gases, you can delete if you don't use them. So If you press here, delete, that's it. And in the cell zone conditions, again, check operating conditions has to be 0, and on fluid, make sure that you have helium chosen, or the gas that you use in your simulation. And boundary conditions, now here, if you didn't define, you can define the inlet. So the inlet pressure inlet, it's the same as in the axisymmetric case. I will not change it, the same outlet and the wall. So if you right click on this one and display, you can see, or you cannot, yeah, because it doesn't like I have I imported that geometry without changing these settings, but it's fine. Everything is okay. So methods, again, second order upwind, we don't change this one. But controls, again, the default settings, and we have the report definitions. We chose pressure outlet. It has updated only the geometry. The name is the same, so it's kept there. And yeah, solution. And again, if it's the first time you are doing the simulation, put here 10 to minus 5, all of this. It's not necessarily to leave the simulation to run until you reach these values, but the default is 10 to minus 3, and I prefer to have as low as possible here. So, okay. Alrighty, now we initialize the flow. If everything is okay, you'll get no error here. Now this value, it's a bit high from my experience. It should be lower, but is fine. So that means that tells you how well the simulation will run. Usually here it's I expect about minus 10, but it's okay. Okay, calculation activities, you can save or not. If you choose here 0, it will not save periodically. If you put, let's say, every 1000 iterations, it will save it. And here you can choose how many you want to keep, how many saved results you want to keep. How many iterations actually you want to keep. You can keep all of them or only the last two. It's good to save this data, because if at some point the simulation diverges and you are not there to catch it on time, you can go back, load the last saved data that the solution didn't diverge, and you can change the settings here and rerun the simulation. It saves time, so you don't have to, if you have to run a simulation for days, you don't want to lose all that time. Okay, and now that we initialized, we have to define some surfaces. So if you remember the last time we defined, we took line outs above the nozzle, which was x1, x2, x3. Now the thing is, these are not valid anymore. So if you try to plot something like this, which doesn't really make sense. So if you go to surfaces and select all of these, right click and delete, because we are not the proper ones. So click on plots, set up a new surface, and now we will use line or rake. So for this one, we know the geometry, so y is transverse, x is the height, and z is the transverse in the other direction. So we will want through the center, so z will be 0, and this one we want it from -3 to 3, so the entire domain. And this one, if you remember, we measure the distance of 17,196, so 18,196, and since it's the same height, these are identical. If you'll take in angles or something like this, then you need to calculate how much should be the value here, so that you can take line out in angle. For instance, if you are using the nozzle tilted in your experiment, so you need to know what is the density profile in that direction. Alrighty, so x1, create, now 19 x2, and then x3. I will not take more than 3 this time. You can take as many as you want. It's not limited in any way. Create. Now, if you don't know the limits of your domain, so what you can do is use this one is a surface, and you choose mesh and just press compute, and it will tell you for each coordinate what are the limits of the domain. So in x is 2.196, and y compute -33, and y -33. All right. Now let's plot this to make sure that everything is fine. So this is the density profile. Now it's not the final density profile, because now we just use initialization, so it's very rough calculation. So it's all of these are Gaussian. They should be flat top profile. All right. So now the thing is, so if after you finish the simulation, you can plot here and save this image and use it in your presentations, article or whatever. But also you have the option, if you want to analyze the data using other programs, you know, not Ansys program. So if you choose this and write, you give it a name, and it will save as an ASCII file wherever you want. So if you want in user, you can save it, you know, something like this, and you can save after you give a name. Okay, and it will save there. So let me show you. Now I will open, and this is the file that we saved. Now if you open with Notepad, for instance, you can see here is so each one of these. So this is depending on what you are choosing here. So if these are checked, they will give you these coordinates as well, but in this case they are not checked. So when you write the file, which is here, is not present, only one coordinate is present. So here is the density, here is the coordinate, and this is for one density profile, and after that second density profile, and third, and so on. Also you have the option when you want to export the data, if you really want, you can file and export and data, solution data. So here you can choose whatever you want, and so if you want to export the entire the density in every point inside your domain. So you choose from here, for instance, density, and where you want in interior, for instance, and right, and you can export all the points inside. So in case you want to plot it or extract the data using other programs and so on. So here, okay, so we haven't run the simulation. Let's run it for a bit. So press check case in case you forgot something or you did something wrong. The program will check and tell you what to correct. Check. So here is the error because we used a different geometry. You can ignore it. And here, that's why you have this error. It tells you why, because you had this initially, but you have this now. So, but it's not a problem. And we put here the number of iterations and calculate. All right. I don't know why it's taking so long. Okay, that's weird. Yeah, I don't know what happened. Probably the computer has to be restarted, I guess. Ah, no, it's fine. So now the simulation is running. Here you have the residuals which are going down. And again, remember, you need three criteria to be met to have a finished simulation or a converged simulation. So this should be as low as possible, and ideally shouldn't change anymore as you run the simulation. The second criterium, when you monitor the density, for instance, of the outlet, again, it shouldn't change anymore as you are running the simulation. So it will be just a flat graph. And the last and the most important criterion is, so if you go to reports and fluxes, check the mass flow rate from inlet and outlet. That tells you that the mass is conserved. So when you choose these ones and press compute, the difference between these ones should be less than 1% or as low as possible. So you see now it's really unbalanced. So this is the inlet, this is the outlet, and of course, since it's just the beginning of the simulation, the difference is quite big. But when the simulation is done, this should be very, very close to each other. So there will be a small difference, maybe somewhere here, third or fourth digit. Okay, so this is the simulation. I will just leave it a few more iterations. Yeah, it doesn't update, but actually it's calculating. All right. So yeah, so the simulation is you let it run until it's converged, and you stop it when it's done, and always don't forget to save periodically when you stop it like this. Even if it's saved, it's better for you to save manually, just to avoid any headache. Okay, we wait to stop it. All right, and here again you can plot. You see now the profile changed compared with before, so it starts to be more and more flat here. So if you let it run long enough, you'll see here a very nice flat top profile, and here you can see the density in atoms per cubic centimeter. Now again you can use graphics, so contours. So oops. So now the thing is, you need first to build the surfaces, so that you can do it from here. Set up new surface. So you can use ISO surface. So let's say I want through X coordinate, Y coordinate, so exactly through the middle of the nozzle. So let's check Y, create, and I will not give it any name now. I just want to show you how it's looking like. Now if you go to graphics, setup, and check this and check the surfaces that we had. So the interesting ones are X and Y. So if we choose density, let's say, save and display. Oops. Yeah, so this is the problem. I can't remember at this point how to remove this error. So probably you will have to start from zero to define this settings, unless you can find out how to remove this error. I can't remember now, but if you remove this error, then you can start plotting exactly like you did in the 2D axis symmetric case. So yeah, pretty much this tutorial is finished. If you liked, subscribe, and if you have the means, you can support me. Check in the description how. Thank you.